Hi everyone, my name is Satya and today I'm going to show you guys how to derive the single degree of motion free vibration equation. It's a it's, to put it in a simple word, it's a mass attached to a spring on a friction floor. It's moving by its own. Uh, so it's let me draw a picture first, and so you can guys have a understanding of what I'm talking about. So imagine a floor, and I have a mass on the floor, and let's say this is like a wall, and a spring is attached to the mass, and also there's some friction in here. Usually, friction is everywhere. Friction, look, well, there's a little bit of friction on the ice. Well, there's a lot of friction on the ice, but it depends. So let's call this. This is a mass and spring of friction. Therefore, ice friction flow, and there's a wall. Again, it's a flow. So we're gonna call the mass as M. Mass is equal to M. Spring is equal to K. I'll come back to this K a little bit in about a second, but most of you guys know what's K. And friction is equal to C. So this is one of the important things. Still in mechanical world, it's unknown to many of the people because C is in term this it's defined as Coulomb friction, or like more in like for in general the we usually as surface friction. That's I I know that I have professors who are still researching on Coulomb friction, and it's really hard to predict. Or I don't know what's the extent of their research about, but I'm pretty sure it's interesting, and maybe we'll do a video in the future. So the second part, the second one I was saying is spring. So it's defined by K. So let's like how this all put together, and uh, K comes from Hooke's law. So this is Coulomb friction, and this is mass as mass, and this is from Hooke's law. Hooke's law. Oh yeah, if I made any spelling mistake, I'm sorry. I apologize for before, and also uh, if you hear any background noises, I'm really sorry about it because I'm in my office and there's a lot of stuff's going around me, so I'm really sorry about that. So let's try the equation. So first of all, everyone must know what are we driving the equation for. So we are driving a single degree of freedom system because it has only one mass. Say let's say if I have a two masses, then it will be 2 degrees of freedom. If I have three masses, a 3 degree of freedom system. Well, when it goes about 2 degrees, we usually say multiple degree of freedom. So is the common term in vibrations. And the second thing is this is called free vibration. Why called free vibration? Because it's oscillating by on its own. Well, in generally we pull up mass, then we let it oscillate on its own. So we do have systems like that, but but we will see in the future videos. So for now, this is the basic, this is the fundamental that everyone learns in engineering. So let's draw the equation. To derive that equation, we need to know two things. One is Newtonian mechanics, and differential equation. Newtonian mechanics, everyone get experience in grade 10 for fundamental, like F is equal to ma, that's the basic. Then the differential equation, so there's two set of differential equation, type of differential equation. One is derived by Newton, another one is Euler. So we're going to use both of them because we're going to see two scenarios where we're going to need both of this Newton and Euler in differential equations. So step 1, everything is F is equal to ma. We all know that, that's Newtonian mechanics. So let's write everything in terms of F is equal to ma. So let's start. So mass, for F mass is equal to, we already know the m mass, so we're also going to call this small m because it's the general notation. So mass times acceleration. Now this is the crazy part that most of us know that, so speed is equal to v is equal to x divided by t. So in another way, a fancy way of saying is, so v is equal to dx over dt. So change of distance divided by change of time, and acceleration a is equal to v over t. So a is equal to dv over dt. So let's rewrite everything in terms of a and x and t. So a is equal to dv dt and v is equal to dx dt. So only difference between from here to here is I'm differentiating by a time. So a is equal to d over dt dx over dt. So that's pretty much it. So what I did is I just replaced this v value by this entire thing. So it's a funny way of writing in engineering, so we usually write, so I just multiply together, so like terms get multiplied, and these two are common terms, dt, dt, so dt squared, so like x by x, or x squared. So that's pretty much it in there. So why do I say this is because, so when you have dx over dt, in mathematics it's allowed to write d dot. If I derived it again, so let's say dx dt, I'm deriving again, so I'm allowed to write dx double dot. So I could go triple dot. Well, usually we don't go above 4 dot. If it comes to a 4 dot, let's say d over dt divided by d over dt divided by d over dt divided by dx over dt. 2, 3, 4. Oh my god, my handwritings. So it's like this is the fourth derivative of x. So we should write in a bracket 4, like in the power, but it's not exactly power. It's just putting a bracket. It tells it like, oh, is it equal to d 1, 2, 3, 4. So it's gonna be a hassle when you have a d to the x to the power of extra derivative of power 5th derivative of x or 10th derivative of x. Is going to be really hassle. So that's why I put it like that. So next thing. So again, mass in Newtonian way. So F is equal to ma. Now we know mass A is equal to the second derivative of position with respect to time, so x double dot. That's one thing. So now we have one thing. Now I am going to skip ahead to the spring first, then I will come back to friction. So spring. Hooke's law. So what Hooke's law says, So let's say mass is suspended in the air with using a spring, and this is the original position, x is equal to 0. After I pull this out, just gonna, no, without a, oh sorry. So when the spring is at rest, so this is like x is equal to 0 and there's nothing on it. So when I attach a mass, it becomes like, goes down by, right now it's like x is equal to 1 from here. So the difference is, let's say delta x. So after I attach the mass, the spring elongated by delta x distance. So what's Hooke's law says? F is equal to k by x. What is this k is? How much is elongated when the mass is applied? So k is equal to f over x. So that's the Hooke's law. So in here, let's bring back to in here. So for F spring, for this situation, for our original situation in here, so let's say k times x. So only it's differed by distance, not the derivative of anything, and also a spring constant, which will always be given in the exam or example, or definitely will be given, unless if you are doing an optimization problem, then you have to figure out how much the spring constant should be so you can have a less vibration. So that's when we do shock absorbers, like when you do absorber calculation, that's how we calculate that. So that's the spring. So we have F mass number 1, and we have a spring number 3. Only thing we are missing in the middle is the friction. Next page. Friction. So when it comes to the friction, it's a complex theory, but I'm gonna give you the rundown. So this is all you need to know. So F friction is equal to C, the Coulomb law. For in this situation, it's a constant, but in reality, it's a varying number. So sometimes like kinetic friction, like dynamic static friction, plus when you do like a gear transmission or like a cam profile, is even complex than it is. So C times velocity. So this is velocity. So we already established velocity is equal to dx over dt, because x is the first derivative, so I can put like x dot. So F friction is equal to c times x dot. So this is the number 2 equation. So I'm going to read out everything in here below this. So F mass is equal to m double dot, because I have acceleration, mass time acceleration is equal to force. And the second one is F spring is equal to k times x. From Hooke's law, it's like the Hooke's law constant times the distance, so number 3. So at the beginning I said it's a single degree of motion, but also it's like a free vibration. I don't know if I say that a lot. So free vibration. So to have a free vibration, which means there's no forces applied, some of the forces must be equal to 0. So let's write down everything. So if these are the forces that I have, then everything must be equal to 0. So let's write F mass plus F friction plus F spring must be equal to 0. So mx double dot plus cx dot plus kx must be equal to 0. Boo. So I should have said that boo, but sorry. This is the equation that we are looking for. So this is the equation of free vibrating mass that is connected to a spring, and it has a friction overflow. You should when so there's like a differential equation. We have a x to the power due to x derived by the second term, x derived by the first term is a regular x direction. So to solve this equation, uh, in differential equation, we have a pretty simple way that everyone will laugh, but it works all the time. Trust me. So everyone remember this one. So if I have like, let's say, I'm just randomly putting out at this example. So 2x squared plus 3x plus 5 is equal to 0. Solve for x. So what if we write, so a is equal to 2, b is equal to 3, c is equal to 5. So x is equal to minus b plus or minus b squared minus 4ac, everything under square root, divided by 2a, so minus 3 plus or minus 9, 3 squared, so 4 times 2 times 5 divided by 2 times a is equal to 2. So minus 3 plus or minus 9 minus 40, which is actually 36. So 31 divided by 4, but has a negative sign inside because you can square root a negative. So minus 3 plus or minus I root of 31 divided by 4. So this is the solution. So x1 is equal to minus 3 plus root of 31i divided by 4. x2 is equal to minus 3 minus root of 31i divided by 4, everything divided by 4. So that's how we solve a regular quadratic equation. So what we have here for our vibration is mx double dot plus cx dot plus kx is equal to 0. Capiche? Perfect. So let's say E is equal to m and B is equal to c and c is equal to k. I just put this a. You can do the exact same thing. So x is equal to minus b plus or minus b squared minus 4ac, everything under square root, divided by 2a. So minus, instead of b I'm going to put c in here, plus or minus c squared minus 4 times az is m times k divided by 2 times m. So I'm going to rewrite again everything. Minus c plus or minus c squared minus 4mk divided by 2m. So far, so this is like x. So you might be asking why I'm going with this, but you will see at the end like what I'm trying to do in here. So first thing I need to worry about is this one, because I don't know if that's gonna go to 0 or not, or 0 as in like, or it's gonna be either it's gonna be positive or 0 or negative value. We don't know that yet, but the numbers will determine. Number 2 is something we call a damping ratio. So sometimes I don't understand how they derived in the book, but I understand like what are they trying to do, but I don't know why they're trying to do. But at the same time, I understand like what is this giving me and how is it helping me throughout the entire calculation or procedures or in future or other materials. So let's take this value. So c is equal to 4mk. I'm going to set this equal to 0 for just for now. So, let's say I'm going to put a dummy value. So I'm going to put a dummy value called, let's say, alpha. So what the damping ratio tells me is that C critical, so damping ratio because zeta is equal to, am I doing it right? Yeah. Damping ratio is equal to C divided by C critical. So that's a critical value. So that's the damping ratio. So let's go back and make this alpha. Let's just say so let's go back in here and I want to find out what's the critical value that it could have. So C squared minus some critical for mk is equal to 0. So C critical is equal to, so I'm going to take this on the other side, 4mk squared. So C critical is equal to root of 4mk. Now I have this value. So this is the critical value. So critical is usually like sometimes it reaches infinity or sometimes it reaches 0. That's what, because if you have something in 0, then you're gonna have a problem in multiplying and dividing together. Obviously, when you have infinity, that's a huge trouble. You don't want infinity. You want to have something like something you can count or something you can measure. So this is the critical value. So critical value is equal to root of 4 times mass times this Hooke's law, the spring constant. So we could do a small arithmetic in here. So it's like we know it's like 4 is root of like, so root 2 times mk, root of 4 is 2. So another thing, so this is something interesting. We know, so I'm going to go to the next page and do it the other way. So for mechanics, omega. So omega is equal, what is omega? So for in simplicity, I can say, let's say I have like a, this is like I'm pinning a let's say a bar with the radius r, and I'm rotating by this distance, this theta. So the distance traveled in the arc is called arc distance. So let's say it's s. So in mathematics, S is equal to theta times r. Remember, r is constant. So that's the location. S is the distance, is travel. If I want to find the speed, so this is distance. Speed. So remember in the previous page, we say speed is equal to distance divided by time. So we're going to do the same thing in here, but r is constant, so only the theta is going to be changing. So d over dt s is equal to, because we're driving based on time, so r is a constant, so I'm going to put it out. So d theta divided by dt. So this is equal to v, because it's a velocity, or it should not be speed but velocity, but it doesn't matter. R is a constant. D theta over dt is equal to omega, or r times omega dot. In here, when it comes to this mass of the spring, omega is defined as K over M. One day I will do a quick video about why is omega is equal to K over M when we get to Lagrangian points. Until that, we're just going to leave it as in here. So we will get to that later on. It's pretty simple why this become K over M. So let's go back. So O omega squared is equal to K over M. Right now we have C critical is equal to 2 times mk, or root of 4 times mk, but I prefer to use this one. So we can either rewrite in terms of k, or we can write in terms of m. So I'm just gonna write in terms of k. So take this equation and put it right here. So omega squared is equal to k over m. So k is equal to omega squared times m. And this omega is natural frequency. So C critical is equal to 2 times m, which is over here. We're going to replace the k with the omega squared times m. So omega squared times m. So let's do a small thing. So omega squared times m squared. This omega, well, also it's a small note. Omega, it's a natural frequency, so we use omega n. So since the natural frequency, so everything is in the power, so we can simplify this thing. That's like 2 times omega n m, or 2 m omega n. So that's the value of C critical. So if we know the natural frequency, and if you know the mass of the object, we just multiply by 2, that's the critical frequency, no, critical value, Coulomb value, C. So zeta is equal to C divided by C critical. So C divided by 2m omega n. So this is the damping frequency. So zeta is equal to C divided by 2m times omega n, natural frequency. So let's go back to our original equation. So what we said, mx double dot plus cx dot plus kx is equal to 0. Then we use the what's that? I forgot how to call, but it's like x is equal to minus b plus or minus b squared minus 4ac everything divided by 2a. Was it not differential equation? The correct. So x is equal to minus c. So m is equal to a, c is equal to b, and k is equal to c. So I'm going to replace everything by that. C plus or minus c squared minus 4ac divided by, oops, I made a mistake. X is equal to minus c plus or minus b squared. So b is equal to c squared here. Minus 4 times a is equal to mass times springs k divided by everything divided by mass. So let's work this equation out. So what I'm gonna do right now is separate it, so I can divide this by 2m on each side. So minus c divided by 2m plus or minus c squared minus 4mk divided by 2m. Simple. So I just divided by both sides by 2m. So we're gonna do some crazy manipulation in here to make it simple, because what we want to do is destroy the c. We don't want c. We would like to use the previously found term zeta. So we said zeta, the damping ratio, is equal to c divided by 2m omega n. Okay. So let's take out this. So let's rewrite the equation as c is equal to 2 zeta m omega n. Simple. I can replace every c by this value.